Hey everyone, welcome to this year's lecture on causality for AI and ML. So, um, yeah, we gave this lecture, I think, 2 years ago, but we have revised a bit in the meantime, and some things have changed. We will give a bit more focus on like doing things and applying algorithms, like get more on the how to actually do and compute stuff. But today I will just start with an introduction or the motivation. Basically, why do we need causality? Why is it useful? Why is it maybe also required? And particular with the focus on AI and ML, what can we learn from this and where to apply? So the lecture will be held by a group of people. Today, I will present the introduction and probably the main part of the lecture. Tim, Florian, and Matej, who are sitting here, will also give some lectures. Christian, who can't be here today, will also sometimes join the lecture, I guess. But yeah, we will change a bit in who's presenting, depending also on the topic of expertise. So yeah, I'd say let's start. And yeah, present is working perfect. As I said, why do we need causality? Basically, let's start with a more general problem. In everyday life, we often perform inference. We take cues like how this person looks to infer maybe how heavy the packet is that the person is carrying. Also, before like knowing this, we will take actions to maybe yeah to we will adapt our actions to adjust for the things we have inferred. But sometimes, okay, the printer isn't working. Oh, okay. But sometimes we are wrong. So we see sometimes people fool us, we make wrong inferences, and the packet is actually way lighter than we expected. So the question is, or the problem is, where does causality come into play? And why is causal inference harder? Oftentimes, and especially for AI and ML models, they use associational learning. They see correlations in the data and leverage that to make predictions. The problem is that these predictions may be arbitrarily wrong if we look for the causal direction. In case some of you have heard probabilistic graphical models or similar lectures, we might also infer information about the variable v from their children, like factors that are derived from that. The problem is, if we now want to intervene, that means we want to change the downstream variables, we might not be able to influence our target variable because the effects only travel in the other direction. In contrast to that, if we intervene on parents, we will be able to change the target variable and have an effect. And this might be relevant, for example, in reinforcement learning, where you often or sometimes see agents learning spurious correlations. And then if the environment changes, try to intervene here and failing the task to adjust V to a particular value because they can't distinguish cause and effect. And in general, what we will do in this course is that we will use graphical models like already depicted here, which are basically graphs that showcase how causal effects flow through a system. The challenge there is, of course, most of the time we never see this kind of graphs, but we have to infer it from data. And I will just give you a few examples to see why this is hard, and throughout the lecture we will see what we can do to recover these. Right. So in contrast to the previous slide, as I already mentioned, most AI tools maybe don't use causal inference or causal concepts, but they are becoming increasingly more popular to summarize text. They're taking the role of experts or for policymaking. And depending on the errors these models will make, that can have severe consequences if we, for example, adjust for the wrong variables and fail to accomplish particular effects or outcomes we want to have. Basically, these articles are a bit older, although this is quite recent and maybe a bit biased because it's from BBC itself. It says chatbots can summarize articles. They're used for breast cancer prediction or explaining the predictions of models. They're used for fairness and in healthcare. So it's relevant in or used in areas where it's really critical that we get the causal direction wrong, that we don't fall for spurious correlation. And overall, and probably you're using ChatGPT, Gemini, whatever on a daily basis, you often see that they fail to accomplish even simple tasks. Although they're getting better, it's still easy to fool them. So let's start with a very simple example. We observe a correlation between ice cream sales and sunburns. So throughout the years, we record these statistics. We look at economic data. We look at like hospital data or doctor's notes, whatever. And our model sees, well, there is a correlation, but the question is now, what do we do with it? Where is the causality coming in? The first thing we could do is to say, well, maybe it's in the direction that ice cream sales cause sunburns, right? So that means eating ice creams causes sunburns. A model would, on the opposite, infer we should forbid ice cream sales to reduce sunburns and increase the health of our population. On the other way, we could go for the opposite direction and say, well, maybe if we have a sunburn, we get ice cream. Might be true for younger children, for which their parents will buy them ice cream or something. But in general, I think we can agree that that's not the case. And the third option is that there might be some other factor, especially like sunny weather or warm weather, which influences both that we just haven't recorded in our statistics or in our data. And generally, the question is, if we observe such a situation, how do we know which of these effects are in the underlying process? Which of them hold true? And as you saw before, if we only observe the two data points and we make no other assumptions, then correlational guessing is arbitrarily wrong because we just by chance have to pick any of those directions. And your ML models, if they don't adjust for these kind of situations or for like causal direction, if they don't reflect or don't think about it, and if we don't instruct them to do this, they will adapt one of these directions arbitrarily, basically, with this one needing additional data, but still. So maybe the problem is even worse. So you probably heard about the spurious correlation problem, which means that if you have loads of data, just by chance, there will be correlation somewhere. And this is a really nice website. You can go to the link here and look at many other examples. So basically, they took this to the extreme. They collected a bunch of data and like specifically searched for correlations. And some people and some models might infer also a causation. So that's a problem. I think we can be sure that the distance between Uranus and the moon doesn't have anything to do with the electricity generation in Japan. Similarly, although maybe funny, or maybe there is some underlying cause, but the dump waste to die and the number of electronic engineers in Utah is kind of correlated. And here are also the R values. So this one is not particularly statistically relevant, but the one before was. And if my presenter is doing things, put on your tinfoil hats this way. I think we uncovered a secret space mission because that's the Google searches for how to go to space and the Chipotle Mexican grill stock price. And it has a significant correlation. So in your statistics class, you might infer at least that these time series are linked to each other. And I would guess maybe they are not, or via some third factor, maybe a media campaign or something. So generally, as I said before, correlation does not imply causation, although you can make up stuff which might be remotely funny. So maybe we are going back to the more simple case. We assume we have variables and we know by some external information they are causally linked to each other. Then there is Reichenbach's common cause principle, which is already quite old and very well known, which basically tells you, well, I can only have 3 different structures, which means either X causes Y, Y causes X, or there's a third variable involved. And be aware, maybe you have seen it in your statistics classes, this is for the underlying structure. If you condition on a common child of X and Y, you might also get observer bias and other biases which link these variables together in your particular scenario. But we will do that in a later lecture. Yeah. Oh, oops. Oh yeah, I will correct it. Thanks. Yeah, it's like these 3 scenarios. Yeah.
Yeah, could you give an example for where conditioning on a common child of X and Y would?
Yes. Yeah. So maybe it's about then independence, but you could take this classical example in computer vision where you see cows that are always observed on grass or on meadow, and maybe no, they're going there because of a causal link. It's maybe how people take pictures of particular things, right? You say, okay, I look on the internet for a particular object, and I only see like a subset of pictures which look particularly nice. But by selecting only for the nice examples, I'm filtering out all the other variants. I correlate, I don't know, like fancy looking clothes with like famous locations or something. And by that, I get a correlation, although I might observe these clothes somewhere else, or these locations exist without these clothes there. So it's really quite common effect when you start collecting data or curate data sets. But
that's only when they're somehow causally linked?
No, like in theory, you can make up any data sets, right? Where you observe, where you have a subset where a correlation might occur, or where things occur together. If you only select that subset out of the whole distribution, then it seems like for your particular case that they are correlated at least. And you just don't know, is it because we specifically reduced our data set, or is it, because it's in the underlying process occurring naturally. But we will come back to this, and I will have a better example. Sorry for that. Whoa. Okay, that was the presenter with all the stuff it was skipped before. Cool. So a more critical case or interesting case in science might be a similar scenario. We observe the activation of a gene A down here on the x-axis, and we observe the phenotype of, I think it was for a plant, like how it looks, which features it has. And we see that they are correlated. And the question now again is, I want to maybe knock out the gene A, like I want to deactivate it artificially. And my question is, what will happen? Will the correlation continue? Will also the phenotype go to zero? So will the feature vanish? Or will nothing happen? Because maybe the gene isn't linked to A. I think here, in most statistical analysis, we would at least assume that there is a correlation, and maybe we would also assume that it continues if we like change the gene. So in this case, well, we are maybe lucky and it happens. So we knock out gene A and the phenotype, the feature of the plant vanishes. Same example, different gene, and we might get a completely different result because maybe we have a confounder. Maybe here this one is gene A. We changed gene B, but the causal effect didn't travel upwards because A influences B, but on the reverse, not B influences A. So the phenotype, which only depends on A, doesn't change. This is similar to the previous examples, but I just wanted to show something which is more applied, where you maybe do experiments, work with other scientists, and want to figure out how things relate to each other. So again, we have two cases. And just from observing these correlations, the best we can do without making any further assumptions is we don't know. But under different assumptions, and we will show it for causal discovery algorithms and how to identify such effects, it might be possible to recover structures, which then goes probably or most often via the noise distribution and so on. So in the previous examples, and I already spoiled it a bit, so we were jumping right to the conclusion. We had the questions and we were asked to say, well, what is the answer? Will the gene influence the phenotype or something else? But in general, we could do like a scientific method where we observe something, then we have a theory, and from that we derive an answer and check it versus the ground truth in the beginning. And if we are in the field, we are hopefully right with our prediction. But that in the first place requires that we have a model and that we build up this model by discovering causal relations and structures. And only then we start doing inference and estimate the causal effects we get out of our models. So generally, we will use graphical causal models, which is basically saying we use graphs, as I showed you before. And there are like two main types, and I think maybe some people who heard probabilistic graphical models have seen them before. It's causal Bayesian networks or simply Bayesian networks. I think people use them interchangeably, but I always think with causal Bayesian networks that they are showing the true underlying causal direction, that they are structured in the right causal way, because what they are is tables for variables, and each table shows a conditional probability distribution, which tells you, okay, I have the variables if it's cloudy or freezing, they're either true or false with a particular probability. And then I have the variable it is knowing, where for every of these parent variables, so if it's cloudy and it's freezing, I have a 55% of snow. And while this is the true causal direction, I would say, Bayesian networks could also be structured differently, where I say, well, I could say that snowing is only dependent on freezing. And then I get the arrow from snowing to cloudy, where I say, okay, what is the probability of it being cloudy, seeing that it's snowing, for example? Yes.
Is it a feature of the graph that it's not normalized?
Yeah, sorry, I skipped the false probability. So it's only the probability for that it is knowing. Otherwise, the table would be double that size, and you would have the opposite probability that it's not known. So this is basically probabilities for like under the condition of C and F, it is then normalized. So for every of these variable settings, basically the probability sum to 1. But we will have that in the later lecture. Equally, and I find this more easy to grasp maybe for computer scientists or like closer to also ML models, because you can think of them as maybe compute graphs. We have structural equation models, which basically tell you the equations, how variables are computed. And you just start at the beginning. For example, we have rain and sprinkler. You sample random variables at the very top according to some probability distribution. So this is basically random noise according to some distribution. And then you have a third variable, which is computed via some rule or some function, which is basically, okay, the ground is slippery if there was rain or if the sprinkler is on. So basically what we see, I took different examples to make it easier to write down the formulas. But in terms of causal structure, it is the same, because here you also have rain and sprinkler influencing the slippery variable. So these compute graphs, well, it's already in the name, introduce a causal graph, hopefully, if we get the structure right. So getting the structure right, that's actually the main problem, because usually we don't have that. So in recent times, the use of LLMs is becoming more common, and they can read texts and read scientific articles and have memorized a lot of knowledge. So basically, sometimes they can tell you, okay, I've seen this fact before. I know, I don't know, like sunshine causes sunburns or something. But if you have new data, if you're in a scientific field and are doing experiments for which no literature exists, we need to find other ways to recover these structures from data. So the most naive approach would be, well, I know my causal models are somehow structured as graphs. So I could just go and iterate over all the possible causal graphs that I have for, let's say, 2, 3, 4, whatever variables, and just check whether they, or which one of those fit the best, like which structure, which connection of the variables fits the best. And maybe for 3 or 4, maybe also 5, 6, 7 variables, you can do it if you have enough compute. But after that, the number of graphs you have to check for a particular number of variables basically explodes. So we have to be smarter, and the growth of the number of graphs or particular directed acyclic graphs grows super exponentially. So the naive way is not a solution. Yes. Let's assume we have heard, I think it is in lecture 5, how to do causal discovery, and we have a causal graph. Now we want to estimate effects, and for that, and this is the main breakthrough, I would say, in causality or causal research, there is the do calculus, which is a set of rules that tells you when causal effects can be inferred or identified from data, which means I have a causal graph, I have my data, and I can tell which effect or which strength of effect a variable x has on a variable y throughout the whole graph. So maybe something before going into do calculus, you have probably also heard the thing conditioning is not intervening. And if not, I will tell you now. It's a very common effect that basically tells you, okay, we assume there is this causal structure. So we have the sun, which influences ice cream sales and sunburns. And there is a difference between only looking at days where there were no ice cream sales. And on these days, we probably also have no sunburns. Let's say this is just the days in winter, although you can get sunburns. Let's assume a simplified scenario. We got lower ice cream sales, so we get lower sunburns because the sun isn't shining. So for conditioning, we can traverse in the anti-causal direction and see how these statistics change if we only condition on particular subsets. On the opposite, if we were to make a policy, so we are making decisions for the health of our population, and we say, well, we forbid ice cream sales, then it's something different, right? Because now we artificially set this variable to 0 or to some lower number. And by that, we cut the causal relation, because in this scenario, in this intervened scenario, the sun is no longer influencing the amount of ice cream sales. And by that, even on sunny days, we still get sunburns, but the ice cream sales are still down. So overall, the distribution changes. And this is something to bear in mind because it will become important later on, that sometimes we have scenarios actually where those collapse to the same distribution. But in this scenario, for example, it doesn't, and this will make a difference. So, as I said before, do calculus, and this name is linked to Judah Pearl, basically I would say, inventor of modern causality, probably. First, he invented these Bayesian networks we saw before, or you maybe saw already in previous lectures. But apart from that, or after that, he went on to create the do calculus, which basically is not only about modeling statistical distributions in graphs, but also about how to infer causal effects and know when we can do it and under which circumstances. Basically, I think do calculus will be the third lecture, and it gives us some insights on how data is structured or how certain scenarios are structured and which types of inferences we can make. And basically, the most important is for AI and ML models that sometimes seeing is not enough. So there is a so-called ladder of causality, which means we have three different ranks. And the first rank is associational, which means we only observe. The second one is interventional, which means we are doing things. That could be your RL agent, which interacts with the environment. The first one being, okay, we just fine-tune or train a model from a data set we have collected previously. And the third run is counterfactual or imagining, which basically means we go back in time, we replay the scenario, and we think about what would have been if I changed something, if I intervened somewhere, if I did a different action in the past. And the important thing here is that while sometimes these things can collapse in terms of probability distribution, they are different classes with non-zero non-zero overlap, but also there are interventional settings which are non-associational, and there are counterfactual settings which are non-interventional. And maybe let's look more into it. So association is seeing and observing. This is what we did before, right? We were seeing correlations, and we were thinking about, okay, how do causal effects appear in the data? And we came to the conclusion that for some even simple settings, we might not be able to infer the right causal relation. Right, so typical examples are what symptoms tell me about a disease, or what does a survey tell us about election results. So we see data that was collected previously, and we just try to interpret it. Next on is interventions, which is doing. That's where the name of the do calculus comes from, which is basically the question, what if I do something, or how do I do certain things? Basically, where do I need to change things to get the result I want? And this is, for example, the question, if I take an aspirin, will my headache be cured? Or what if we ban cigarettes in a healthcare setting, for example? So we are trying to predict the future outcome of things. The third run, and probably the most interesting or also difficult to handle, are counterfactuals, which is basically imagining it is retrospection and understanding, whatever that means. But it basically tells us or asked us the question, what if I had done something, or why did something happen? So it's linked to attribution, to our understanding of the world, why things happen. And it is now a similar question to before, where we asked, if I take the aspirin, will my headache be cured? Now we ask, would my headache be cured if I had taken the aspirin? So the difference here is that for the former question, we maybe don't know particular unfoldings of the future, but when looking back, we could have known a lot of variables. We know how the outcomes went. We know how maybe environment noise, what happened to us in the last days. And maybe it makes it easier for us to determine environmental factors, which then also influence the outcome we observe, the actual outcome. And so we have maybe more information, if we can infer it, to go back, change this one variable. Let's say we had not taken the aspirin, and now we take it, and then replay the whole system again, and at least try to estimate what would have happened. That's on its own is also a difficult step, because like inferring all the environmental factors can be hard. But this is really the question about why did things happen. And I think Paul argues in his books also that this is what makes humans or certain animals and maybe also in the future machines intelligent. The ability to reflect and ask the question of why did something happen. So as I said before, the maybe sad message is that according to do calculus, without making certain assumptions, some queries cannot be solved from pure observation. However, the do calculus tells us for a certain scenario if something can be answered and how it can be answered. So for certain graphs, if we look at them, if we know we have observed certain variables, we can infer causal or treatment effects. And this is also only a subset, right? Maybe what they mean with identified means you want a point estimate. You want the exact number that, I don't know, some new medication has on like suppressing a disease or the symptoms of a disease. But sometimes maybe it's also enough to only know is the new drug or something working, right? We don't need an exact number. We just need to, okay, it's working or not. So sometimes even if the do calculus tells us, oh, it can't be fully identified, maybe we are lucky and at least we can estimate the bounds of like the minimum and maximum effect range. And maybe they lie fully in the positive or fully in the negative domain so that we can at least have a direction of if our medication will be successful, at least help. And saying that some queries cannot be solved from pure observations then means, okay, we are not completely lost and can't do anything about it. But usually we need to do experiments, we need to do randomized controlled studies, we need to intervene on the system, and sometimes this this might be unethical or unsafe, so we need to be careful with that. But the thing is, this is basically the scientific method where you are a scientist, you have a theory, maybe you have not yet enough data, but you perturb your system a bit to get enough variation to identify how things relate to each other. Yes.
If you strictly assume you are in a position to generate data, you collect more data, or can you do this with an existing data set?
For which
these data sets not able to generate.
You mean now the doing part? Yes, and that's exactly the problem, sadly, because for doing, and we saw that before, it is not enough to just condition. It is not enough to like doing by conditioning, which means we cannot just simply take a data set and maybe filter particular subsets out of it to get an effect that is really intervening. Because doing means we need to actively intervene on the system. We need to collect new data that breaks some of the causal links, which basically means we break some of the correlations in the data. We change the distribution. And this is eventually what makes the effects identifiable. So I think we will just make a short excursion to some related fields or like how causality was treated in the past. So it's really an old, very old concept. So the ancient Greek philosophers already had this thing of universal causation, which basically tells you nothing happens without a cause. So everything that becomes or changes must do so owing to some cause. For nothing can come to be without a cause. It's 3060 BC by Plato. And this already tells you, like, even without our fancy statistical models, without like computers or whatever people were thinking about cause and effect way before, because it's so natural. It is how we make sense of the world. Similarly, causality in physics is very important because time basically structures how things evolve, how we certain effects travel through a system. Causes always precede their effects. And if we then also think about general relativity and these kind of things, the limit of effect propagation, we can also see that it's not only a temporal effect, but also that the past light cone, which means how far can effects travel for a certain amount of time, play a role here. So we won't be going further into this area, but at least sometimes if we have data, especially if we have temporal data, it makes sense to already use this prior knowledge to not make our causal discovery algorithms discover all the links that we want to have. But sometimes if we have different time steps, we know causal effects can't go back in time, and we already can implement these constraints into our systems to help them identify the causal graph. And also in cognitive science, as I said before, it's something very natural to humans. And I took this example from Tobias Gerstenberg's paper, where it is about they show participants of a study to balls that are like moving towards each other. And the question basically is, does ball A prevent or help ball B go into this goal here at the end? And they also did it with eye tracking. And what you see is that participants not only look at the ball and wait for the end of the video sequence to make their prediction, but they also look ahead. Their eyes go to positions where these balls will be in the future or might be in the future. And this tells us maybe something also about what are our expectations, what do we think will happen. And also then it helps us, of course, to say, well, if ball A wasn't there, ball B wouldn't have gone into the goal, because I basically simulated that it would have gone somewhere else if not for A. And similarly, we can, if we have identified causal effects, use it for algorithmic recourse and fairness, basically saying, how can I, if I'm in a situation where I maybe make unfair decisions, maybe I'm a judge, I observe, I get tired over time and make mistakes for very complex cases. We can use these causal models to rectify this, to maybe find a new strategy that prevents me from doing these mistakes. Basically, this to do the hard, complex cases first and not wait until the end, until you are unconcentrated or something. So yeah, the same thing is for medicine, where basically the tobacco industry claimed for some time at least that maybe smoking doesn't cause cancer, right? Because they wanted to sell their products, their cigarettes, and they had all kinds of theories. For example, well, it might be some gene that makes you susceptible to smoking or to adapt smoking, and also is the cause for cancer. So they claimed, well, if we sell cigarettes or not, it doesn't matter, because it's not our cigarettes, but it's inherently the genes. And the question is, how do you argue against that? Like, how will you come up with a theory or a model or some sort of argument to falsify these claims and get what is now known as evidence that smoking does cause cancer? Yeah, and of course we will do this via or with causal tools. And so if all of this looks boring and you're more interested in your Instagram accounts or something, you can also mine a lot of causal effects, reverse their order, and post flat jokes on the internet or something. But yeah, maybe that's not something we will do extensively in this course. I would say we will do a short break and then continue in 5 minutes. Okay. So now let's go to the second part, which is a bit more focused on actual machine learning and AI models. And basically, it is to maybe give some insights. How well do ML models today handle causality? And if my presenter is working. Whatever. Okay. So basically, ML is omnipresent, right? It is in our smartphones. It improves video recordings. It is used for AI assistance. In recommender systems, if you buy things, what items you get shown. It's a lot of statistics still, but also more and more AI. And the question is, we have now language models, we have generative models for videos and images. And do these models really understand what they're doing? Are they just like memorizing stuff, or do they really know how causal effects travel? And the main thing here is that usually these systems do not interact with the world, right? As we discussed before, they only are trained on data sets which are collected before. And some of these data might be sufficient to identify causes, but maybe some of these data isn't sufficient and it has spurious correlations, or it has some sort of biases which the models memorize without recognizing that some factors are or should be independent of each other. Basically, our question is, do these models really understand what they are doing? And for example, I just asked Gemini 2.5 for like an artistic impression of some causal graph of a black box model or machine. I mean, I wouldn't interpret too much into it, but also this graph somehow looks weird, and I would doubt that it is actually related to whatever this machine shows. Yeah, it shows you some directions, it shows you some arrows, also some like dotted lines, which might be hidden confounders or something. But in general, it is really easy to fool them, or they make mistakes maybe humans wouldn't make. So example I often use, and which is quite nice to look at, is basically we take an image editing model and task it to change this image into night. So make it a starlit night was the prompt. And Stable Diffusion 1.5 basically learned, well, if it gets dark, we should turn on the lights in the house. Also, this is some sort of correlation, right? And it assumes, okay, maybe someone is living there. Maybe if no one would be there, it would also be okay to turn or to leave the lights off. But it is at least a possibility and not causally wrong that this happens. So we see these correlations in the training data. Most of the night image have the lights on. So actually, I would be very surprised if the model would have generated a image with the lights off, because then basically the whole image would just be pitch black, which you don't really often see on the internet, right? So if you collect data sets, it's mostly that lights are on, and this reflects in models. Opposite to that, we could also say, well, not make it dark and it turns on the light, but we could say, please turn on the lights. And now it gets interesting, because now the model has learned the correlation. Well, if there's night, there are lights, but it has also learned, okay, if there are lights, then I should make the image dark. It's again this correlation we see in the data, because if you see a lit up house or something, it's usually dark. But from a causal perspective, so I think we can do the experiment. And if I turn off the light, well, it's still light outside, and the sky doesn't suddenly go black. So, I mean, still, it might be what we want from our models. If we say, well, add some lights and so on, we might want to have that they are visible in the image, and that the model exactly does that. But maybe we don't want to have that in all cases. So the question is, can we control this behavior? And has the model learned only this correlation, or can it do different? And for that, if we, for example, ask Gemini now, it has probably also been trained on loads of data available on the internet. But if we ask it to turn on the lights, it only does this. It does a minimal intervention. Basically, it turns on the light without going into the anti-causal direction or using this statistical correlational link to make it, or to not make it, into a night. So that worked quite well, although it added a window, but hey, you can't have it. So the thing is, depending on your plans, you might or might not train these generative models. But what I want to tell you is that this can happen to your everyday, to your small models, even to your regression models. So assume, like, a very simple case, you have 3 variables and you want to predict the variable B from the other variables A and C. And basically how the problem is structured is that the variable A is some random noise distribution according to some Gaussian with standard deviation. And B is the same as A plus some Gaussian noise. And C again is the same as B plus another Gaussian noise term. And basically the difference here is that from A to B, we have a very high variance for the noise distribution. We have a lot of noise. And from B to C, we have only a bit of noise. So basically, this link is high noise, this link is low noise, and probably you can expect what will happen if we now just train a simple linear regression on this. Oh yeah, maybe look at the data, right? So A is the blue line, which is the cause of B, which is the orange line, and B is the cause of C, which is the green line. And what we clearly see is that B and C are closely correlated, so they closely follow each other. And A does so too, but with a lot of error and margin. So now we do linear regression. We put this time series data, like for every time step, we want to infer B from A and C. And basically what we see is that our model completely disregards A because it has so much variance. It is such a noisy connection. And it puts almost all the weight on C for going in the anti-causal direction to infer B. Even the intercept has a higher value. Okay, I mean, these are multiplicative, these are additive, but still, it's clear that our model prefers C. And depending on how you shape the amount of noise in the links, these values might vary, or it might also be that a model uses A and C, like with 0.5 weights of 0.5 to infer this value. And for the observational and in distribution setting, this is actually fine, right? This is as long as we only want to predict and we don't want to change the system. We want only have some observation, maybe some images to classify. We know there are no like bigger changes happening on the outside, and we are fine with just classifying. Then this model is okay, right? It will infer B from C, and we are happy. The problem becomes, what if we want to actually do something with the with the data and with our prediction? And actually, that is what sometimes is missing. So oftentimes it is taught, oh yeah, it's so cool. We can have a really high accuracy, and our model can leverage all these sorts of like statistical relations and so on. But what do you do with your classification? What do you do with your prediction? Maybe also in medicine, if you want prescribe some medication or similar, then it is really relevant to not only think about the observational case where nothing happens after, but we need to think of, okay, what will now happen if I intervene on C? If I give a medication that suppresses fever symptoms or that suppresses some sort of virus, will just lowering the temperature make the fever go away? Or do we like change the thing and nothing happens because we intervene here, we cut the causal link, but actually we should have intervened on A and lowered the temperature, killed bacteria, whatever. So in your models for prediction, it is okay to leverage statistical correlations because it can make your model better. Because it is also clear, if we maybe go back to this, under the assumption that this model holds, it is perfectly fine to use C to infer B. It is only a problem if we cut this last link. In this scenario, well, using A to infer B, we can do it, but we will get a higher error. We will make more mistakes because of the noise in between. So it is actually reasonable to use C here. But we need to be aware that if we change things, if our agents interact with the world, then things might have changed, might change. We will drop out of distribution, and we somehow need a way to reflect this in our models and in our agents, and structural causal models are a way to do this. Yeah, and as before, it's not only your linear regression models, it is also your neural network, which, like, if you dump them down, if you make them really small, are basically linear regressions, but you see the same effects there. Right, then another thing is shortcut learning. What you often see or get taught in computer vision courses is this classical example of, oh, well, you want to classify some image, and you get a class of horses, and your model becomes really good at classifying them, like 99% or whatever, like maybe 100% at classifying horses. And then you look at the gradient activations or activations of your model, and you see, well, it actually doesn't look at the image contents or at the horse, but what it looks for is that you compose your data set of like many different data sets for the different classes. And your horse data set simply has some credits or some text in the lower left corner. And of course, it is easier now for the model instead of looking at the horse and distinguishing it in shape and size and whatever, because that's a very complex concept from other classes, to simply look for the text. If it's there in your data set, well, it's easy. It's a horse. If not, it is not. But as soon as you deploy this model, it will fail in the real world because your smartphone usually doesn't add this text whenever you point it at a horse. And yeah, this is then the problem, right? A car, although it has horse powers, you can easily fool it by predicting all kinds of images to be horses by then also adding this text. So you can also adversarially attack these kinds of models if you find these shortcuts in these models. Yeah, I already talked a bit about natural language, and this is, I would say, some exciting development of the recent years that basically, for now, we only looked at data. What can we learn from data? How do models infer correlations or causes from data? But the other format is that we now also have natural language, which is used in machine learning in your AI models. And these can similarly have the same information as your data, right? So you can say, well, altitude, the higher up you go, the colder it gets. And you can do the measurements and where you are on a mountain and see this at least a correlation from which you might infer a causation. But you can also go to the Wikipedia article of your choice and just read this information somewhere, right? Then still the question is, do you trust these sources and whatever? But in terms of information, it is equivalent. But here we still have to do the step of mining this information out of the data. And here we just have to understand how text is structured, but it directly tells us what is the causal direction. So we might want to leverage that too as background knowledge when doing causal inference. So overall, you will hopefully develop AI models and you're responsible, right? So in this course, we will teach you the limitations and what can be done from observational data, the cases where we might not get any further with only observations, where we need to intervene and what it means, where it can help us. Then, as I showed you before, avoid all the pitfalls of correlational shortcut learning, of spurious correlations, and so on, which is really telling you we will teach you how to avoid wasting your compute by thinking about the data before, identifying these correlations and eliminating them, or structuring your models in a way that they don't fall for these correlations and don't predict cars as sources. Yeah, overall, will your healthcare model forbid ice cream sales? That is the question. And yeah, maybe to end with a quote for this section: to build truly intelligent machines, teach them cause and effect, also by Judah Pearl in the Book of Why, which I highly recommend reading. So let's move on to the logistics of the course, how it's structured, what we will do over the semester. So you probably already saw it in Toucan. So it's a 3 credit point course. The lecture, you have found it here, is always on Friday, 9:50 in this room. We will have one lecture. Since it's a 3 credit point course, we will have no separate exercise sessions. We might or will do a short recap at the start of every lecture, and also hand out from time to time. We will try to aim for every lecture, but let's see. to also have exercises which are not mandatory, right? Because also credit points are linked to the time we can, you officially have to complete this course. So this is basically really to get your hands on, like calculate some stuff, like get to know how algorithms work, but they are not mandatory. You can use them for preparing for the exam, but we will also have no bonus because of that. Then the rest will be a classical lecture. And as we are doing at the moment, the lecture will be recorded. Maybe we will also record the exercises and recap, but let's see. And usually we will not do live streaming. We weren't sure how many people will show up in the first lectures, but we might or might not do live streaming. We still have to decide on that. Of course, yeah. Then the recordings will be uploaded, obviously, but it may take some time because we have to edit them a bit and so on to make them ready for upload. So the grading will be 90 minutes or 60 minutes.
No.
I think it will be a 90 minutes written exam at the end of the semester. I think the date for that is the 18th of March. I think it might change, but that's the date for now. Yeah, we will hold the course in English, but feel free to ask questions also in German if you want to. Okay, so most of you probably have found it. We have a Moodle course on the Informatik module. Please register on your own. We have a forum for questions, and we will upload the weekly exercise sheets. As I said, they are not mandatory. You can download them. You can have a look at them. You can also discuss answers with us. But we will probably not have the solutions right away, or maybe not have them and only discuss in the lecture, or have them only at the end of the semester. But yeah, this is really to discuss, to ask questions, and to get the slides and recordings. Yeah, also for thoughts, feedback, use the Moodle forum if they're of general concern. If you have particular questions on like scheduling exams because you're away or whatever, write a mail to me or any of the other lecturers. And yeah, maybe are there any questions on the format, how the lecture will be structured? Okay. Is there something in Zoom? No. Seems fine. Yeah. Okay. Yeah. So just a brief overview of the AI and ML lab. So basically, it is led by Professor Christian Kesting. So we have about 40 PhD students working on all sorts of topics, not only causality, obviously, but general AI, generative models, time series. I don't know, like the whole spectrum. But we also have a particular causality subgroup, which is Matej, Florian, Tim, and Nicolas, who is not here today, and me. And we focus basically on causality and related topics. And in case you want to do like your thesis or have some idea for a project or something, feel free to reach out to us. So basically that's the very broad topics we're working on. So it's meta causality, basically how models change. Then tractable causality, which is how to do inference in causal models efficiently. Obviously causality and LLM, because yeah, that's now the very interesting case where we not only have data, but like other information, and we can use them as basically oracles to predict causal relations. but also continual causality, which might be interesting for recommender systems or similar, where you might deploy an online system and maybe a recommender system, and it has to adapt how trends and things change over time, and how to teach that to your ML models, but also to how to adapt your causal graphs according to that. And obviously, if we are talking about LLM, it's all agentic now. But also, since Nicolas is together or is at Bosch, we are also interested in large-scale causality because internally, oftentimes you have really big production lines, and maybe you want to create digital twins of those. And the question is how to do it in a good manner, that they are correct, that you understand what the system is doing. And also if some faults appear, how do I trace back where they come from and identify the location of the faults within my production process using a causal model. Right. So just a brief comment on that. So we have no formal requirements. It would be helpful if you have a good understanding of Bayesian probabilities, or maybe heard probabilistic graphical models before. Although in the next lecture, we will give a recap on that, and we will refresh your memory, or basically just tell you how to handle these models. Also, Tim told me that from the probabilistic graphical models course, which is held also in this semester, there will be a refresher exercise thing after, like next week. We will give the recap on PGM. And after that, from the PGM course, there will also be an exercise or refresher session. If you want to join that, feel free. Yeah. Other than that, so we will not recap the basics of deep learning. So most of the time, we will assume that you know at least how to train basic neural networks, maybe have some insights how LLM works, but we will mostly use them as tools and not dig too much into their internals. And similar for computer vision, like I showed you, we will sometimes work with visual data because it's more fun and interesting, and show you some applications there with respect to representation learning. So if you maybe heard of VAEs before and now know how they work, that would be helpful, but it is not required. Yes. So basically, we heard Paulian causality before, and this is the main part of the lecture, or this is what it's all about, because this theory, these structural causal models are so powerful. We will have a first part that basically is about the basics, the statistics, how to work with causal models from data. Then we will go into machine learning and show how can we apply these causal concepts to our ML models, how to train them, how to maybe also structure them such that they become causal, or at least understand a bit what they're doing. And finally, we will do a part on general applications, which is explainability, reasoning, fairness. Basically, if we have such models, what to watch out for, how to use causal models in more broader applications. Yeah. So basically, this is how the lecture will go. Yeah, I will give you some time to read, but it's really the topics we will cover, mainly one topic per lecture. So first, we will have, oh, this is actually the second lecture, but a refresher on PGM. Then we will go into from the statistical models to structural causal models, recap on the causal hierarchy, what it means like formally, and look at the rules of do calculus, how to actually apply them and what they are. Next, because I already told you, this is the kind of interesting rung of the causal ladder. We look a bit more into counterfactuals, their implications, how to derive them. There is a particular structure called twin networks, and also how to do backtracking. Yeah, like how to reason counterfactually, how to infer what would have been or could have been. Then next, more already going into more practical thing. It is causal discovery from tabular data mainly. There are different types of algorithms that are suited for particular scenarios, and I think Florian will tell you how to apply them, when they work, and what they can do. Yes, and then again, something with uncertainty. In case some of these approaches fail, if the do calculus is not exact, we still can sometimes do some effect estimation, and we will have a lecture for that. Right. Then more on machine learning, although it doesn't appear as an explicit term here. We will look particularly at representation learning, which means if I give data to my model, what representations will it learn internally, and how are these representations related to each other? So before that, we will do something on causal abstractions, which mainly is how to cluster causal variables. How do my causal models change if I now have visual data? Because in images, I don't have this nice tabular data with variables measured, but before doing any causal inference, I first need to see which objects are in my image, like where are they, how big are they, what's their color, and so on. And I first need to learn that from the data before I then can do anything causally related. Right. Then we will go a bit more into how to do it with interventions, without interventions. As I said, sometimes observational data is enough if you have the right observational data. And then we finally do neural causal models, which is basically models which are particularly designed to account for causal relations and causal structures. So up here, it's mostly about we use our classical ML model and feed them the right data. And down here, we will see how to modify some of these models such that they have these causal structures already implemented. Yeah, and finally, LLMs and causality. What can we do? Where are the pitfalls? And where are we heading here? Yeah, finally, general topics, causality and fairness. As I showed you before in the example, linked to explainability and root causes, like we observe some behavior we want to avoid. We have some failure cases in our production processes. How do we handle that? How do we track back and find the root causes of failures? How to adjust for unfair decisions or biases in our models and in our everyday decision making. Basically, then we will go to meta-causality and actual causality, which is all of the above usually assumes more or less static causal models, apart from obviously intervention. But sometimes you have models that change over time. For example, climate models or weather throughout the year. Different causal effects might appear or vanish, and we will see how to model and do things here. And in the end, we will have a recap and question session where we'll just show you some other related insights, and you have the chance to ask questions. In terms of materials, yeah, we will provide the slides, we will provide the recordings, but there are some books which I would highly recommend. Of course, none of them are required, right? It's only for reading further into the topics, and we will give you all the necessary information in the slides and in the lectures. But if you want to know more, the book Causality by Julia Pearl is basically the book to go for. It's in terms of machine learning, yeah, a bit older, let's say. Still, it's 2009, and it has all the basics that are required for particularly the first part of the lecture in there. Then a bit more modern, it's Elements of Causal Inference, which I find is a bit easier to read for computer scientists. It's a bit more specific on the models they are using and presenting and the things they are showing, but it's a good introduction. So yeah, that's interesting. If you're actually interested in how to make inferences, how do things come to be, looking at attributions, there is a subfield called actual causality, and the book is named the same by Halpern, which might be interesting for like the particular lecture. But apart from that, is really nice to read and has good examples on how to handle several cases and infer some causal relations or attribute causes. Finally, there are some online courses already. So there's Freddie Neal's online course on causal inference, which is really good for like picking up a specific topic. So basically, it's one video per concept. So if you want to refresh your memory, maybe before the exam or while learning, I would recommend like going there and just checking if there is a video on that, because it's really nicely made and the examples are very illustrative. Similarly, from Jonas Peters, there's another lecture on causality, maybe a bit in the way of how the book is written. You will find some of the examples we present here also shown there, and maybe it's just good to have another perspective from our lecture. Again, the books are not required, but at least for the online courses, they're free, and I would recommend that you just have a look into it. And basically, that's it. So again, ending with a quote from Julia Pearl, as X-rays are to a surgeon, graphs are for causation. So basically, they help us to break up our black box models and reveal what our models maybe are internally thinking, or at least how they are structured. And that's it for today. Thank you. And if you have any questions, please ask them.